Okay, hello everyone. My name is Jianxi San. I'm a graduate student of Purdue ECE. Today I would like to give a lecture on ROC curve and its analysis. Okay, so if you want to learn more about this lecture, or if you want to see other lectures on different topics, please visit the website here. Okay, so this lecture is organized as following sections. Firstly, I will give an introduction about ROC and ROC curve. Then a simple example is investigated to derive the idea of the ROC curve. In order to scientifically represent ROC curve, some statistics terms will be introduced in the definition section. So how to use ROC curve to analyze the classification process and how is the performance of the ROC curve will be given in the last section. Okay, so let me start with the introduction. So basically, what is the ROC curve? So ROC represents the receiver operating characteristics. And what is the ROC curve? That is the curve represents the relationship between the hit rate and the false detection rate. And how to use ROC curve. So the plot of ROC curve illustrates the performance of a binary classifier system as its discrimination threshold is varied. Okay, so let me start to introduce how to derive this ROC concept from a very simple example. So let's consider a diagnostic test for a disease. There are only two possible outcomes, which are positive and negative. A patient takes the test and gets either positive result or negative results. So we can assume the testing process as a classifier and the disease-related trait of a patient is the input feature vector, and we pack them up as a multi-dimensional feature vector. Since the result go to either positive, which is green, or the negative, which is red, the testing process is basically a binary classifier system. Okay, so if we apply the general Bayes rule, which is used for classifier, in the classifier, G1 and G2 are the product of the density of each class and the class prior. A general discriminant function G of feature vector can be written as the difference between G1 and G2. By comparing the value of G with 0, we can choose class 1 or class 2 accordingly. And the threshold can be calculated by reversely solve the denomination function at the result 0. But here's the question. In practical, we don't know the class probability density. If we use Bayes rule, we have to find a way to estimate the density from the training data and calculate the threshold. We may ask the question again, is there any way to find out the threshold from training data without estimating the density? Actually, ROC curve came to rescue the world. So let us come back to our disease testing example and see how to derive this ROC method. To make things easier to demonstrate, we assume our feature vector is one-dimensional value. The red curve is the product of the negative class density and the negative class prior, while the blue curve is the product of positive class density and the positive prior. So let us look at what will happen when the threshold position is actually moving. The classification process chooses negative and the positive class based on the feature value is less or larger than the threshold. From the figure, we can see the threshold value will affect the performance of the classifier. Intuitively, you can think about that. There must be a threshold value that can optimize the classification accuracy. So in other words, there's only one option, optimize the threshold value, that can optimize the performance of this classifier. Okay, before we introducing the way to find out the optimal threshold, let's look at some new terms that are used to represent the ROC curve. Okay, the first one is the blue area. Is the blue area here. So this area is classified as positive, and in reality it is indeed positive. So they are correctly classified. So we name this region as true positive. Okay, so the second region is the small red region here. So this region belongs to the negative curve, but it's classified as red. This is classified as blue. This is not correct. We name this region as false positive. Okay, so the third one is the big red region here. So this region is classified as negative, and they are indeed negative. This is correct, and we name it true negative. The last term is the smaller blue region. This region is classified as negative, but in reality they belong to the positive curve. This is not correct, and we name it as false negative. So all possible classification results can be summarized in this table. For this two classes example, all the four possible results corresponds to four evaluations we just defined. Patients are diagnosed as normal or abnormal on the negative and the positive results from the testing classifier. Of course, some of the results we have from the classifier are not correct. Okay, so here are two statistic terms that we need to define. So the first is the sensitivity. Sensitivity is the ratio between the true positive and the summation of the true positive and the false negative. So if you look at the previous graph, with the two curves, this is the big blue area over the area under the blue positive curve. So that is the ratio of this area over the area covered by the blue curve. In other words, sensitivity represents the number of the class positive data points classified as class positive over the total number of the class positive data points. So let me repeat that again. So the sensitive is basically the number of the class positive data points classified as positive class positive over the total number of the class positive data points. And this is accurate actually, so we name it as give it another name, which is a hit rate. So the second term is the specificity. So specificity is the ratio between the true negative and the summation of the true negative and the false positive. So if we go back to the curve again, this is just the big red area over the area covered by the red curve, which is the negative curve. It is also easy to see that 1 minus the specificity is the number of the class negative data points classified as class positive over the total number of the class negative data points. Because this is wrong classified, so I'll give another name to the result of 1 minus specificity as false detection rate. This graph demonstrates how the value of classification threshold will affect the area of the four regions we just defined, which are Tn, Fn, Fp, and Tp. Based on the observation, we can see that the hit rate and the false detection rate will correspondingly change as the threshold value changes. So the ROC analysis is the process of finding the optimal threshold by evaluating the result of the hit rate and the false detection rate.